In this lecture, we are going to solve some problems related to optical fibers. Let us look at this first problem here. An optical fiber without cladding is having refractive index of 1.5 and a diameter of 50 micrometer. What is the approximate pulse broadening per kilometer on this fiber? Find the number of modes in the fiber and also find reduction in number of modes if the fiber is immersed in water. The wavelength of light is given as 1.3 micrometer and the refractive index of water is 1.33. We all know that when the light propagates inside an optical fiber, which is having a diameter much larger than the wavelength, then you can use the simple ray model for finding the estimate of the pulse broadening on the optical fiber. So, let us consider a simple optical fiber cross section like that. That is the axis of the optical fiber. When a ray is launched at the maximum possible angle, the ray will be refracted inside this optical fiber and it comes here, and since this is the maximum possible launching angle here, the ray actually goes along the edge of the optical fiber or the interface between the core and the cladding. Now, since there is no cladding for this fiber, the refractive index N2 for this is equal to 1. The refractive index of fiber, which is glass, is N1 and that is equal to 1.5. This angle is theta 0 maximum, that is the ray which is barely totally internally reflected from the core cladding boundary. Now, we know that when the light is launched inside this, there is one ray which can go along the axis of the optical fiber, which is like that, and the extreme ray which will go in this direction. Since the refractive index is constant inside the optical fiber, the velocity for this ray and this ray is same, which is c divided by n1. So, the velocity of light for all the rays travelling inside the optical fiber, which is equal to c divided by n1. Then, as we have seen earlier in our discussion, that the time difference of arrival between these two rays is given as delta t, that is equal to n1 upon n2 c, which is velocity of light, multiplied by n1 minus n2. Now, since the cladding is not there for this fiber, n2 is equal to 1. So, n1 minus n2 is 0.5, n1 is 1.5, n2 is 1. So, that gives us the time difference is 1.5 divided by n2, which is 1, multiplied by velocity of light c, which is 3 into 10 to the power 8 meters per second, multiplied by n1 minus n2, which is 1.5 minus 1, which is equal to 2.5 nanoseconds per meter. Since we have used the velocity of light in terms of meters here, the unit for this time is nanoseconds per meter. Normally, when we talk about time difference inside the optical fiber, it is given in terms of per kilometers. So, the time difference delta t will be this multiplied by 10 to the power 3 if you want to convert the meters into kilometer. So, this is 2.5 microsecond per kilometer. So, that is the difference in the arrival of these two rays and that is what essentially gives what is called the pulse broadening on an optical fiber. The second thing which is asked here is that how many modes are going to propagate on this optical fiber, and when the fiber is immersed inside the water, how many modes will be there. So, what is the reduction in the number of modes? So, we can see here, first of all, as we know approximately, since the fiber is multimode, the number of modes are approximately given by V square by 2. So, first we have to calculate what is the V number of the optical fiber, and as we know the V number of an optical fiber is 2 pi by lambda into numerical aperture into the radius of the optical fiber. So, the numerical aperture for this optical fiber is square root of n 1 square minus n 2 square, which is equal to square root of 1.5 whole square minus n 2 is 1. So, square of that is 1. So, this is 1, which is equal to 1.118. So, the V number for this optical fiber is 2 pi divided by lambda, which is given as 1.3 micrometers. So, 1.3 multiplied by 1.118 multiplied by the radius of the optical fiber. It is given that the diameter of the optical fiber is 50 microns. So, A is equal to 25 micron. So, we get the V number of the optical fiber is about 135, and the number of modes on this fiber then is approximately equal to V square by 2. So, that is 135 square divided by 2. So, that is approximately equal to 9112. So, as you can see, without the cladding, since the numerical aperture is very large, the extremely large number of modes propagate on this optical fiber. So, this fiber is extremely multimode, about 9,000 modes are going to propagate in this optical fiber. Second thing which is asked is that when this fiber is immersed inside the water, what is the reduction in number of modes inside the optical fiber? So, first thing one should note is when the fiber is immersed inside the water, then the refractive index of surrounding now is increased from 1 to 1.33, because the refractive index of water is 1.33. That means, now the n 1 minus n 2 is reduced, and as a result the numerical aperture of the optical fiber is reduced. So, now in the second case, when fiber is immersed in the water, the numerical aperture will be square root of n 1 square minus n 2 square, but now n 2 is not 1, but n 2 is 1.33, that is the refractive index of water. So, this is 1.5 whole square minus 1.33 whole square, and that is equal to 0.6936. So, if I substitute now the numerical aperture, which is 0.6936 inside this expression, the A is still 25 micron, lambda is 1.3 micron. The V number in this case now would be 2 pi divided by 1.3 multiplied by 0.6936 multiplied by 25, and that will be approximately 83.75. So, the number of modes in this situation are approximately V square by 2, and V is this now. So, this is approximately about 3507. So, when there was no cladding, that time approximately 9000 modes were propagating. When the same fiber is immersed inside the water, since the refractive index of surrounding medium is increased, the V number of the fiber is gone down, and because of that the number of modes are reduced to 3500. So, now from approximately 9000 modes, the modes have reduced to about 6500. So, difference of these two, that is the reduction which we have in number of modes. Naturally, one can ask a question at this point of time, what happens to this mode which were earlier propagating inside the optical fiber? The answer is very simple. The earlier, the higher order modes which were confined inside the optical fiber, now when the fiber is immersed inside the water, become leaky mode, and because of that the power corresponding to those modes essentially radiates out, and as a result the number of modes actually decrease inside the optical fiber. So, this is one of the simple problems one can see related to the optical fiber. Let us look at the second problem now. Now, in this problem, it asks determine the normalized frequency at 0.8 micrometer wavelength for a step index optical fiber having 25 micrometer core radius. N1, which is the refractive index of core, is 1.48, and N2, the refractive index of cladding, is 1.46. It is also asked what is the cutoff wavelength for the TM01 mode. Now, this problem is a very simple problem to solve. First of all, as we know that first we have to find out what is the normalized frequency of this optical fiber, and normalized frequency is nothing but the V number of the optical fiber. So, we have here normalized frequency, which is the V number of the optical fiber, which we know is 2 pi by lambda into the numerical aperture multiplied by the radius of the optical fiber. The numerical aperture, as we have seen in the previous problem, is square root of n1 square minus n2 square. So, this is 1.48 square minus 1.46 square, and that is equal to 0.2424. So, the V number for this optical fiber, that is 2 pi divided by lambda, and in this problem the lambda is given as 0.8 micrometers. So, this is 0.8 multiplied by the numerical aperture, which is 0.2424 multiplied by the radius of the optical fiber, which is 25 micrometer. So, this gives the V number is 47.6. So, the first part of the problem where it asks to find out the normalized frequency of this optical fiber at 0.8 micrometer. The normalized frequency is nothing but the V number of the optical fiber, and for this fiber at 0.8 micrometer, this normalized frequency turns out to be 47.6. The second question which is asked here is, what is the cutoff frequency for the TM01 mode? And as we all know that on the optical fiber, the first mode which propagates, that is the HE11 mode. After that, you have a bunch of modes which start propagating. TE01 mode start propagating, at the same time TM01 mode start propagating, and that happens when the V number of the optical fiber is 2.4. So, the frequency at which the V number becomes equal to 2.4, that is what is called the cutoff frequency of that particular mode. So, in this case, if we make V number equal to 2.4, and ask at what wavelength the V number will become equal to 2.4, we can work backwards and say that V number to be equal to 2.4. The wavelength which we want to find out, which is lambda, substitute into this expression here the numerical aperture, which is 2424 multiplied by the radius of the optical fiber, which is 25 micrometer. So, if I just invert this, I will get the lambda, which is 15.87 micrometer. So, as you can see that for most of the operating range of wavelengths which is used for optical communication, this fiber is going to remain the single mode optical fiber. Let us look at the third problem now. Now, this problem is a little interesting problem, not a very practical problem, because this is not really related to optical fiber in that sense, though the principles involved here are exactly same as what we find inside the optical fiber. But this problem helps you in understanding how the rays actually are totally internally reflected inside the optical fiber and the light is guided. So, what this problem says is, this problem says a glass tube filled with water is used to guide light along its length. What is the numerical aperture for the guiding system? Refractive index of glass and water are 1.5 and 1.33 respectively. So, look at the configuration which we are having here. We are having a tube of glass and the tube wall have some thickness. So, we have this is the tube. So, if I take a glass tube and just cut it by plane, that is the way the cross section of the tube would look like. So, this is glass, and here the tube is filled with water. So, here the refractive index, let us say this is the axis of the tube, the refractive index here is NW, which is water. The refractive index here is of glass, which is NG, and here the refractive index is air, which is N is equal to 1. So, this is equal to N equal to 1. Now, in the first look, it may appear that if I try to launch light inside this, since this system will look as if you are having a core here, which is water, and you are having a cladding, which is glass, and then you are having a third medium, which is air. Now, the water refractive index is 1.33, the glass refractive index is 1.5. Therefore, in first look it may appear that if I compare this system with the optical fiber, the refractive index of the core, which is 1.33, is lower than the refractive index of the cladding, which is 1.5. So, in first look it might appear that this system will not be able to guide light along its length. However, if you really think little deeper, you will see that the question is not saying that the light will be guided inside the water. It is simply saying if you treat the whole tube as a system, then can the light be guided inside this system. So, let us look at how the light is going to propagate inside this. Again, we can consider a simple ray model, because the size of the tube is much larger compared to the wavelength. So, let us say I launch a ray from here inside the tube, inside this water. Now, since the refractive index of water then is higher than this ray will bend like that. Now, at this point, since this angle cannot be greater than critical angle, because this refractive index is smaller than this, the ray is going to be refracted, and now this is denser medium compared to this. So, the ray is bent bending towards the normal at this point. So, the ray will go something like that. Now, if this angle at this location, since this is 1.5, the refractive index is 1 here. If this angle is less than critical angle, the ray will simply get refracted in the air. If this angle is greater than the critical angle at this interface, which is the glass air interface, then the ray will get total internally reflected, and then will come something like that. Then again it will trace the path back exactly like the way it is going, and then it will go on the other side, again go to this side of the glass, again will get total internally reflected, and so on. So, inside the water, the ray is going to propagate, get refracted inside this glass, and if this angle happens to be greater than critical angle, then there will be total internal reflection at this interface. There is no possibility of total internal reflection at the water glass interface, but certainly there is a possibility of total internal reflection at the glass air interface. So, now one can ask a question, what is this maximum angle possible, this theta 0, for which the light will be guided inside the structure? That means, this angle becomes equal to the critical angle, or in that situation this ray actually will travel along the interface between the glass and the air. Now, it is a simple Snell's law application on the different interfaces. So, first of all, let us say if this angle is theta 1, this angle is phi 1, this angle is phi 2, and this angle, since this ray is going along the interface, this angle is 90 degrees. So, if I apply the Snell's law at this interface, and here the refractive index n is equal to 1, I have sine of theta 0, that is equal to n w, which is the refractive index of water, multiplied by sine of theta 1. I can apply the Snell's law at this interface, which is the water glass interface, which is n w sine of phi 1, that is equal to n g, which is refractive index of glass, sine of phi 2. And this angle is phi 2. So, this angle also is going to be phi 2. So, if I apply the Snell's law at this interface, which is the glass air interface, I will get n g sine of phi 2 is equal to this n, which is equal to 1 sine of pi by 2. So, at this interface, this will be n g sine of phi 2, that is equal to n, which is 1 sine of pi by 2, which is equal to 1. So, I see from here that the n g sine phi by 2, that is equal to 1, and n g sine phi by 2 is n w sine phi 1. So, from here we say this is also equal to 1. So, from here I can calculate sine of phi 1, that is 1 upon n w. And phi 1 is nothing but pi by 2 minus theta 1, or theta 1 is equal to pi by 2 minus phi 1. So, now the numerical aperture for this system, which is nothing but sine of theta 0 when this angle is maximum, corresponding to the ray which goes on this interface, that is equal to n w sine of theta 1, which is sine of pi by 2 minus phi 1, which is n w cos of phi 1, that is equal to n w square root of 1 minus sine square phi 1, and sine phi 1 we have got 1 upon n w, So, this is equal to n w square root of 1 minus 1 upon n w square, which is equal to square root of n w square minus 1. And since n w is given as 1.33, I can substitute the value of n w 1.33. So, the numerical aperture for this system would be equal to 0.87. So, what is interesting in this problem? The interesting thing in this problem is that when the light is trying to go inside this, though the refractive index of the inner region is smaller than the refractive index of the outer shell, in the conventional optical fiber sense, you have a cladding here, you have a core here, and the core refractive index is smaller than the cladding. But if you are having a medium outside, which is air, then the light is not guided inside the core, but the light can be guided at the cladding air boundary. So, even if you are having a core refractive index smaller, there is a possibility of guidance of light at this interface, which is the cladding air interface. That is one. Second thing to note here is the total internal reflection is going to take place at the glass air interface. So, as far as the guiding mechanism is concerned, that is the refractive index which is going to come into picture, because that is where total internal reflection is going to take place. But if you look at the numerical aperture, nowhere the refractive index of glass comes into picture. Only the refractive index of water, where the light tries to get in, only that medium plays a role in deciding what is the maximum angle possible. So, the interesting thing in this problem is that even if you are having refractive index smaller in the core, but if the cladding is of good quality, then the light may get totally internally reflected at the cladding air interface, and there may be guidance of light inside the core cladding structure together. Of course, this is not a conventional way the light propagates inside the optical fiber, but just for sake of understanding, we can see here that even in this kind of system, the light can be guided inside a glass tube or a capillary tube or something like that, where the refractive index inside could be smaller than the tube material. So, this is another interesting problem. Let us look at another problem. Now, in this problem, the V number of an optical fiber is 5. Considering all degeneracies, find how many modes will propagate in the fiber. Now, we all know that when the optical fiber V number is given, we can very quickly calculate the number of modes propagating inside the optical fiber, and that is V square by 2. However, you must remember that this expression, that the total number of modes propagating inside the optical fiber is V square by 2, is an approximate expression. When the V number is large, this approximation is reasonably accurate, but when the V number becomes small, then the accuracy of the expression is not very good. So, one can ask a simple question. If I have a V number which is, let us say, 2. Now, if I consider V number 2, then the V square by 2, this expression will give me simply V is equal to 2. So, V square is 4 divided by 2. So, it will give me 2 modes. Whereas, now if I look at the BV diagram here, I can see very clearly that for this V number, there are no 2 modes propagating. There is only this mode which is propagating. If I consider degeneracies, of course, I will get 2 modes. But the point is that when I make the V number small, then that expression which is V square by 2 may not give you an accurate result for the small V numbers. And as the V number becomes larger and larger, that time you may get a reasonably accurate results for the number of modes propagating in a multimode fiber. So, let us see now. it is said that the V number of this optical fiber is 5. That means, firstly, whatever modes are less than 5, V number 5, those modes are going to propagate. So, if I take this line here, this is the V number 5, then these modes are going to propagate inside this optical fiber. So, let us jot down what are the number of modes which are going to propagate inside this optical fiber. So, as you can see here, this mode is HE11 mode, then you are having a TE01 mode, then you are having a TM01 mode, then you are having a HE21 mode, then you are having a HE12 mode, HE31 mode and EH11 mode. So, let us write down that if I look at the BV diagram for V number 5, how many modes from the BV diagram will propagate. So, firstly, we will get a mode which is HE11 mode, then I will get TE01 mode, we will get TM01 mode, we will get HE21 mode, then you get HE12 mode, you get HE31 mode, EH21 mode. So, you see here from the BV diagram which you have seen, these are the 3 which are here, there are 3 modes in this and there is a 1 mode which is propagating here. However, when the question is asked, it is said very clearly that including all the degeneracies, how many modes are going to propagate. That means, though you are having these indices 1, 1, it tells you the intensity distribution of the electric and magnetic field inside the optical fiber, there are still the degeneracies because of the polarization of the modes inside the optical fiber. So, let us ask a question, what are the polarization degeneracies or the angular degeneracies corresponding to each of these modes. So, as you can see, if I look at this diagram here, that is the field distribution which you are going to get for the HE11 mode. Now, as you can see here, the electric field is oriented this way, but there could be electric field which is perpendicular to this, which is orthogonal to this electric field, that will also have the exactly identical intensity distribution, or in other words, it will also have the propagation characteristic identical to this direction of the electric field. That means, for this mode, we are having 2 possible orientation of electric field, which will have exactly identical propagation characteristics. So, this mode has a degeneracy. Degeneracy of 2. What about TE01 mode? For the TE01 mode, the field distribution is given like that. Now, since the field is oriented this way, no matter what orientation you have, you get actually the same field distribution. That means, for this the degeneracy is 1, because there is only one field distribution which you can get for TE01 mode. So, for this the degeneracy is 1. The same is true for TM01 also, because if you orient this, you will get the same field distribution. So, you get degeneracy for this is 1. What about HE21 mode? I have this is the field distribution for HE21 mode, but if I take this field which is this way, if I change it to this direction, where this was completely horizontal, this is radial, I will get a orthogonal field distribution corresponding to this. So, I will get a degeneracy corresponding to this mode, right, which is factor of 2. So, I will get factor of 2 degeneracy for this. Similarly, you will get a factor of 2 degeneracy for this, and all these things which are going to have the variation, which are going to be similar to these ones, you will get degeneracy which are factor of 2, factor of 2. So, now I see that total number of modes, if I ask which are going to propagate inside the optical fiber with a V number 5. From the BV diagram, we see there are about 7 modes which will propagate, but there are different degeneracies for the different modes, and if I put the degeneracies, I will see the total number of modes which are 2 plus 1 plus 1 plus 2 plus 2 plus 2 plus 2. So, this is you will get 2 plus 2 4, 6, 8, 10, 12. So, you will get total number of modes which are going to propagate from this is 12. How does it compare this with the approximate relation? If you had calculated by using the approximate formula, the number of modes in a fiber will be equal to approximately V square by 2 and V is 5. So, this is 25 divided by 2. So, that is equal to 12.5. So, you see the formula is reasonably accurate, but when the V number is very small, that time the formula may give you little error, but the results are reasonably accurate. The formula predicts about 12.5 modes, maybe you could have rounded off to 13 or you can round it off to 12, but this formula gives you the 12, which is exactly same as what you get considering various degeneracies, right, of the modes corresponding to HE11 mode, TE01 mode, so on and so on. So, this is another problem which where one can calculate the number of modes which are propagating inside an optical fiber. Let us consider another problem. Now, this problem is related to the dispersion on optical fiber. It is given that for an optical fiber, the pulse delay t over a wavelength range is given as t is equal to a plus b lambda square plus c lambda to the power minus 2. Show that the dispersion at a wavelength is given as lambda times s 0 divided by 4 bracket 1 minus lambda 0 by lambda to the power 4, where s 0 is the slope of the dispersion as a function of wavelength and lambda 0 is the 0 dispersion wavelength. So, let us look at this problem. So, what is given here? Given is pulse delay t, that is a plus b lambda square plus c lambda to the power minus 2. Now, we all know the dispersion is the derivative of this delay as a function of wavelength. So, we have dispersion d, that is dt by d lambda, which if I differentiate this with respect to lambda, that will be equal to 2 b lambda minus 2 c lambda to the power minus 3. Now, it is given that a wavelength lambda 0, the dispersion is 0. That means, d is equal to 0 at lambda equal to lambda 0. So, if I substitute this into this gives us 2 b lambda 0 minus 2 c lambda 0 to the power minus 3, that is equal to 0. Or from here we can find the relationship between b and c. So, this gives b is equal to c lambda 0 to the power minus 4. The second thing which is given there is that the slope of the dispersion at this wavelength lambda equal to lambda 0 is given by parameter s naught. So, we can calculate the slope of dispersion. which is d by d lambda, and this is given as S naught at wavelength lambda equal to lambda naught. So, if I take the derivative of this as a function of lambda, we will get 2 b plus 6 c lambda to the power minus 4, lambda naught to the power minus 4. So, from here I can solve, I can substitute for b in terms of c. So, from here I will get S naught is equal to 2 c lambda to the power minus 4 plus 6 c lambda naught to the power minus 4. So, from here I can find out what is the value of c. So, the c is equal to S naught by 8 lambda 0 to the power 4. And if I take this value of c and substitute into this will give me value of b, which is S 0 upon 8. Then I can take this value of b and c and substitute into the expression for the dispersion. So, we get the dispersion d as a function of lambda, that is equal to 2 b into lambda. So, this is 2 S naught upon 8 into lambda minus 2 c, which is S naught upon 8 lambda 0 to the power 4 lambda to the power minus 3. So, if I just simplify this, I will get the final expression, which is S 0 upon 4 into lambda 1 minus lambda 0 upon lambda to the power 4. So, that is what is asked here, that if the pulse delay was given by this expression, then the dispersion on the optical fiber can be written in terms of the 0 dispersion wavelength, which is lambda 0, and the slope of the dispersion curve at the 0 dispersion wavelength. Now, many times the dispersion characteristics of an optical fiber is approximated by this kind of relation, and the dispersion then on the optical fiber can be calculated in the vicinity of the 0 dispersion wavelength by using this simple formula. So, this is more like a practical problem, because that is the way many times the dispersion characteristics are approximated, and one can calculate the dispersion right on the optical fiber at other wavelength in the vicinity of the 0 dispersion wavelength. Let us look at another problem on the dispersion on the optical fiber. In a single mode fiber, the normalized propagation constant is given as b is equal to 1 minus e to the power minus v, where v is the v number of the optical fiber. If delta for the optical fiber is 0.01, the core refractive index is 1.5 and the core radius is 5 micrometer, find the wavelength at which the fiber will have maximum dispersion. Now, though the problem may not give you a number which are very realistic numbers, but this explains how one can approximately find the dispersion if the dispersion curve can be expressed in some analytical form. So, as we know that the dispersion curves starts with 0 for the normalized propagation constant b, and when the v number is very, very large, the normalized propagation constant b becomes equal to 1. So, the curve looks very similar to this kind of exponential curve. So, in this case it is given now that b is 1 minus e to the power minus v. Now, as we have derived earlier for the waveguide dispersion, the d is given as minus n2 upon c lambda v d2 bv by dv square. So, since the b is given as 1 minus e to the power minus v, we have bv, that is v minus v e to the power minus v. So, for this we can get d by dv of bv, that is equal to 1 minus e to the power minus v minus v e to the power minus v, and d2 by dv square bv, that is equal to e to the power minus v plus e to the power minus v minus v e to the power minus v. So, that is equal to 2 minus v e to the power minus v. We can substitute this into the expression for the dispersion. So, the d is minus n2 upon c lambda v into 2 minus v e to the power minus v. Now, we have to find out the wavelength at which the dispersion becomes maximum. Now, from this expression we can note few things here. Firstly, that when v is equal to 0, the dispersion is 0, because this quantity is 0. So, the dispersion goes to 0. When v is equal to 2, again the dispersion is 0, because this term will go to 0, and therefore, dispersion will be 0. Thirdly, when the v is equal to infinity, that means when the v becomes very, very large, this quantity becomes close to 0. So, this again the dispersion will go to 0. So, this, if you are having the normalized propagation constant given by this expression, the dispersion characteristics is fairly complicated. The dispersion is 0 at v equal to 0, the dispersion is 0 at v equal to 2, and the dispersion again is 0 at v equal to infinity. To find out where the dispersion will go a maximum, first we have to find out the location where the derivative of the dispersion goes to 0 as a function of the wavelength. So, we want to calculate when d by d lambda is equal to 0. Let us look at this problem on birefringence on optical fiber. As we know that since the optical fiber is not absolutely circularly symmetric, the two orthogonal polarization propagate with different propagation constants on the optical fiber, and because of this the two polarizations undergo different phase change. Now, two orthogonal polarization together can generate a state of polarization, and if the phase change is a function of distance on the optical fiber, the state of polarization keeps on changing as the wave propagates on the optical fiber. So, this problem essentially is related to that an optical fiber has a birefringence of 10 to the power minus 6. Now, what is the birefringence? Birefringence is the change in the refractive constant for the two orthogonally polarized modes on an optical fiber. So, that change in refractive index is 10 to the power minus 6. A circularly polarized light beam is launched in the optical fiber. At what distance from the input point the beam will be linearly polarized? Will it become circularly polarized again? That is the question. So, now as we said that if you are having the optical fiber core, the two fields which are perpendicularly polarized, let us say this field is E x and this field is E y. They travel with different velocities, or in other words they see different refractive indices, effective indices. So, let us say this one looks at refractive index which is n x, and this one sees the effective index which is n y. So, the phase constant for this mode, horizontally polarized mode, is beta x, which is beta 0, which is the propagation constant in the free space, multiplied by the refractive index which this polarization sees, which is n x. Similarly, the propagation constant for this polarization is beta y, that is equal to beta 0, multiplied by the effective index which this polarization sees, which is n y. So, the phase change when the modes propagate on the optical fiber, then the phase change between these two polarizations is equal to beta x minus beta y multiplied by the length which it travels along the optical fiber. Substituting for beta x and beta y, we get beta 0 n x minus n y into length. Now, this quantity is nothing but the birefringence that is given as 10 to the power minus 6. Though the wavelength is not given, for calculation purpose, let us assume that we have a lambda which is equal to 1.5 micrometer. So, let us take lambda is equal to 1.5 micrometer. Now, if the launched mode is circularly polarized, that means these two polarizations, linear polarizations, have equal amplitude, and the initial phase difference between these two is equal to pi by 2. That is the condition we have for a circularly polarized wave. Now, if the wave has to become linearly polarized, then the phase difference between these two polarizations should be 0 or 180 degrees. Or in other words, if the phase change which these two polarizations are undergoing, the difference in the phase change, if that is equal to pi by 2, then the initial phase change of pi by 2 is nullified by the phase change which is going to take place or added. So, either the phase change at that distance will be equal to 0 or 180 degrees. That means, if this phase change when it becomes equal to pi by 2, the original circularly polarized wave will be converted into a linearly polarized wave. So, we can ask a question at what distance this happens. So, if I put the phase change is equal to pi by 2, that is beta 0, which is 2 pi by lambda, birefringence which is given as 10 to the power minus 6, and we want to find out what is the length at which this is going to happen. So, from here we can calculate lambda equal to 1.5 micrometer. So, you get L is equal to 4 pi will cancel. So, you get lambda upon 4 into 10 to the power 6. Lambda is taken as 1.5 micrometer. So, you can substitute that. So, this is 1.5 into 10 to the power minus 6 divided by 4 into 10 to the power 6. So, that is equal to 0.375 meters or 37.5 centimeters. So, that means, if a circularly polarized wave is launched inside this optical fiber at a distance of 37.5 centimeter from that location, the circularly polarized wave will be completely converted into a linearly polarized wave. Now, if I keep moving further, the phase difference again will change, and after the same distance there will be accumulation of pi by 2 phase. That means, from this location where the wave was completely linearly polarized, if I move 37.5 centimeter away, again the phase difference between these two polarizations will be equal to 90 degrees. That means, the wave will become again circularly polarized. So, at this distance we get linear polarization. If I make the same distance again, that means, if I go to a distance of 75 centimeter, then I will get circular polarization again, because the phase difference will be equal to pi by 2. If I again move 37.5 from that location, again I will see linear polarization and so on. That means, assuming that the two polarizations undergo the same amplitude change, we will see that the wave goes from linear polarization to circular polarization to linear polarization periodically, and this period is 75 centimeter, where the initial polarization is again restored back. So, the answer to the question, will the wave be converted to circular polarization again? The answer is yes, it will be again converted to circular polarization, and if we move further again, the wave will again be converted to linear polarization and so on. And in between these two locations, the wave will be elliptically polarized. So, what we see here is that because of birefringence on the optical fiber, as the wave propagates, the state of polarization goes on changing continuously, and the wave from the linear polarization can go up to circular polarization and so on. So, in those optical communication system which are polarization sensitive, one has to worry about the state of polarization of the outcoming light, and that is where one has to take the fiber which are what are called the polarization preserving fibers, because those are the fiber in which the state of polarization will not change as the light propagates on the optical fiber. But if you consider a normal optical fiber, even with a small birefringence as small as 10 to the power minus 6, you will see a periodicity in the state of polarization. So, here are certain problems which we have seen today, which are related to the basics of optical fiber. We saw the problem related to the V numbers, we saw the problem related to the cutoff frequencies, we saw the problem related to dispersion calculations on the optical fiber. We also saw the problem how the rays are propagated in the core and the cladding, and we also found a situation where even if the core material refractive index is smaller than the cladding, but if the outside medium is air, again the light may be guided not at the core cladding interface, but at the cladding air interface. So, this problem essentially gives you more on hands on experience on solving the problems related to the basic light propagation inside the optical fiber.